When a capacitor is charged or discharged directly with the voltage source, there will be a significant charging loss, and soft charging reduces this loss. The proposed design achieves capacitor soft charging without the need of additional split phase control. As you can see, all flying capacitors are charged or discharged with an inductor in series, which ensures that no voltage mismatch across the flying capacitors during phase transition and achieving self-charging. During the charging and discharging phase of capacitors, the inductor current produces voltage ripple across flying capacitors. Although it is not shown here, in practice, there should be voltage ripple, as I will show later. There are 4 charging-discharging paths in the design: AB1, AB2, BB1, and BB2. And because of the number of capacitors on each charging path is different, as a result, the voltage ripple across each capacitor will be different. The capacitor voltage ripple can be measured by looking at the voltages at node Vx1, Vx2, Vx3, and Vx4. As shown here, if the ripple, as shown here, you can see that the ripple in switching node 3 and switching node 2 is double the amount of the ripple in switching node 1 and 4. However, if the ripple voltage is kept small compared to the input voltage, the difference in ripple is insignificant. Moreover, the feature of flying capacitor soft charging is preserved regardless of the inductor current mismatch. The paper also presents a prototype of the design. Here is a picture of the prototype as well as the major components used. The waveform of the prototype converter is on the left, and expected operation is on the right. You can see that it operates as expected, and from the experimental waveform, we can see the effect of capacitor voltage ripple shown here. This is a summary of the efficiency of the design. The proposed design operates as 333 kHz for maximum efficiency, with a maximum output of 100 amps. You can see each line represents a specific conversion ratio. For example, this green line is 48 volt to 1 volt, and the blue line is 48 volt to 5 volts. And here are some sample efficiency data. So it has 90.9% efficiency for 1 volt 30 amps, 93.6% for 2 volt 35 amps, and 95.3% for 5 volt 40 amps. This performance is superior to the previous works in the area in many ways. This is a comparison to the previous works of point-of-load converters. As you can see here, the proposed design, which is the third column, it has a much more flexible conversion ratio as compared to the DIH converter. It also has a much higher conversion ratio than the series capacitor buck converter. Also, the proposed design has a much higher output current and output maximum power. Moreover, the proposed design does not need the capacitor sizing and split phase control, while achieving a similar efficiency at a higher output power than the other two designs. In conclusion, The proposed point-of-load converter aims to answer the need for a high-performance converter for the infrastructures of the fast-growing telecommunication industry. The design makes use of multiple flying capacitors and series inductors to achieve natively built-in self-charging of the capacitors. And it does not require complicated split phase control or capacitor sizing. The end result is a point-of-load converter that, when compared to previous works, has a much better flexibility and a higher performance and efficiency.